idea saying where what the distribution is like. If it is in particular a continuous quantity, then it might have something like a uniform distribution. Well, the value of A can be any of the numbers that that needs to be. Then if you are a patient, they come and see your nose and see that you have a nose. Now the probability of flu changes. This is the posterior distribution of flu given the evidence that you have run into. Okay? And so in general, probability A given B is true might look like that kind of a distribution. The only thing is they're all distributions, so this and this, both of them should have area under the curve 1. That's it. Right? And later on I will say probability A and B is true and C is false. The distribution might look like that. Keep this in your mind. You want to think in terms of distributions. What you are really doing is the distribution of the variable. Okay, if it is a Boolean variable, it becomes very simple because if you know its true value, then you know 1 minus that is a false value. If it is already multi-valued, then you don't know. You have to give all the values, the probabilities for all the values. If it is continuous, you have to give the entire function. And what you're really doing, as the evidence accumulates, you're computing these posterior distributions. Okay, that leads us to, I don't know, those of, I must have mentioned this in the extended session, the second Bayesian joke, which is that how do you tell a Bayesian? You can tell them from their posteriors. Okay? Because Bayesians are all into posteriors. You can get away with this kind of stuff in the AI classes. Anyway, so now by the way, what we did in doing the Bayes network really was you essentially used a rule called the chain rule. It's the other chain rule. It's not the chain rule of differentiation, it's the chain rule of probabilities. Okay? And the chain rule of probabilities is very useful because if you notice what happened was you found the probability of A and B is probability of A given B times probability of B. Right? How do I know this? Because probability of A given B is defined as probability of A and B by probability of B. So I just extremely cleverly took the denominator, put it next to the other side, and then I have chain rule. This doesn't look all that impressive, but I can make it more impressive by then saying probability of x1 to xn, joint distribution of x1 all the way to xn. So it's not just A and B, it's x1 and x2, etc., xn. I can write this, right? I can write this essentially in this way. Xn given everything else times everything else, which can then be written as xn minus 1 given everything else left times that stuff, and so on. You see what I'm saying? This is the chain rule. Right? Basically, I just wrote it here that probability of x1 to xn is probability of xn given x1 to xn minus xn given x1 to xn minus 1 times probability of x1 to xn minus 1. Which now you can use this and apply the chain rule again, until you will be left with one probability. You were wondering, where did I do this magic with the Bayes networks? Wait, Bayes networks? That's basically the background. Because I want you to see that before you leave. Two things. One is, why is Bayes network, Bayes a big deal? A nicely handwritten thing, but I already told you. So you can read this. Okay? The other thing I will come back to in a minute, maybe in the extended session, which is about normalization, which is very useful to understand. But since before the extended session, I want people to understand how you get these numbers. Why did we do this? The stuff that you all yelled at the top of your voice saying, P, the probability of rainy, the cloudy and not rainy and blah, 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 is you told me the numbers that I need to multiply. How did you figure that out? Why is that right, in essence? You figured it out the other way. But why is that right? Well, it turns out that given that you understand that the Bayes networks essentially capture conditional independences of the form, a node given its parents and its ancestors is the same as that node given its parents. Okay? In general, conditional independence is of this type. Any conditional independence assertion will be of this type. PA given B and C is the same as PA given B. That's a conditional independence assertion. Right? And so, if it turns out, but basically all I'm saying is, if in fact B is connected to A and C is connected to B, then PA given B and C is the same as PA given B. And that number will be here in this game. Two things are done. Do you understand what I'm saying? The semantics come from the conditional independence assertions, and the numbers come from the CPTs. Okay? Now, the only thing is that you need to write the chain rule in the right order. Now, notice that the chain rule, x1 to xn is the same as xn to x1, is the same as any permutation of x1 to xn. Right? So, I am okay to apply the chain rule in the topological sort order. There is nothing wrong with it. And if I apply it in the topological sort order, then I will be asking the probability of a node given only its parents and ancestors. And whenever I ask the node given parents and ancestors, you remove the ancestors and just assume the parents. So the first writing is correct just by chain rule. The second writing is correct because of the Bayes network topology that you said is true in your probability distribution. Putting those two together, you get the numbers. Get that, right? So, in particular, I am in this, going back to this, our old network. Going back to our old network, I'm trying to compute J and M and A and not B and not E. Okay? I want to write it essentially in such a way that, in a sort of a, I want to apply the chain rule in the anti-topological sort order, so that the last things left will be burglary and earthquake, for which the priors are directly given, because they have no parents. So that's what I wind up doing. So I will start by saying, I'll write the first one, this thing as J given M, A, not B, not E, times M given A, not B, not E, times A given not B, not E, times not B given not E, times not E. This stuff, what I just said here, this is true for everybody. Correct? For any Bayes network. Any Bayes network. It doesn't depend on Bayes networks at all, it's just applying chain rule. And then I will basically simplify this. J given M, A, not B, not E is just J given A. And similarly, M given A, not B, not E is nothing but M given A. A given not B, not E is nothing but A given not B, not E. And not B given not E is the same as just not B, because it has no children, no parents. And then P not E. Those are the numbers. You multiply those numbers and you get the stop. Okay? So I'll stop here for the regular session. I will go until 15 for the extended, and then right after 15 I run. Otherwise I will. Yeah, we'll talk about it. questions? Okay, anybody leaving should leave fast. Run. Okay. Now, let's do a couple of things that I want you to do, such that we can continue next class about the rest of Bayes network inference. The first basically is this idea of normalization in using Bayes rule. This is something people assume you know, and so I should tell you once just so that you are not surprised. Do you understand what I'm saying? It's just a simple idea, but basically people assume everybody knows this. So remember this, PD given S is PD S given D times PD by PS, right? That's true. So the probability of disease given symptom is symptom given disease times probability of the disease by probability of the symptom. Okay, of these numbers, symptom given disease is the textbook knowledge. That's the causal knowledge. Probability of disease is what's called the prior knowledge, prior on the disease. What's the probability that in a random population, people have this disease? Do you see what I'm saying? And this one is the probability of symptom. Of these numbers, I already said this number is in the textbooks. This number, in the city you are in, you know the prior. What's the prior for having flu in Tempe in June? What is the prior for having flu in Tempe in January? What is the prior for having flu in some other place for something, a different month? All of these you could essentially estimate. That's called prior. Okay? What is harder to get is probability of the evidence. Because probability of the evidence is actually not a particularly robust thing. Remember, the evidence would be runny nose. That, even in Delhi, in a couple of days, the smog lifts and people are not having runny nose. Right now, it's like 1.0. Everybody has runny nose. But a few days later, hopefully, nobody has runny nose. You see what I'm saying? So it's a much less robust number. So the question then is, can I not be forced to estimate this? Because this is, if I estimate this, and as I estimate, I have to assess it by asking people around doing experiments. If I estimate this, it's going to change all the time. And then I have to re-estimate it. I have to re-estimate it. Do you see what I'm saying? So the question is, can I somehow get by without doing probability of evidence? Well, you can. If instead of directly just computing probability this is equal to true given symptom, if you both compute this is equal to true given symptom and compute this is equal to false given symptom, those two numbers have to add up to 1. Do you see what I'm saying? So if in fact the disease can be 15 different values, then those 15 values have to add up to 1. So the idea, the smart idea, if you hate computing the denominator, assessing the denominator. By the way, very important to understand in probabilities that computing versus assessing. Assessing means you go into the real world, do experiments, and basically take the number of things of the numerator by number of things in the denominator. Computing means you take your probability rules and compute the values of the other probabilities. Right? So assessment of this can be very, very costly because you have to actually go into the real world and do experiments. That's the point of the hardness of polls. Basically, people have to call and nobody answers the phone. And as soon as they say we are polling, forget it, I don't want to. I want to know who is going to win, but I would not take part in the poll. Do you see what I mean? That's what we say. That's what free countries say. So the point, of course, is if I cannot, it's not the computing. We're not talking about computing PS. We're talking about the difficulty of assessing P of S. And you are changing the difficulty of assessing P of S into costlier computation. And that's a trade-off we are willing to make. Do people understand this? It's an extremely important thing to understand. Because computation, we have enough computers. Calling people is the painful thing. Okay? And so what basically you do is, if you are willing to compute the full distribution of the disease, here you only need to know whether the guy has disease true. Or maybe if disease can have 15 stages, you only need to know whether the disease, the terminal stage. So that you can say, start packing. But you really want to, but you can't just do that, you have to compute the full distribution. What's the probability that this guy is in terminal stage given the symptoms? Terminal -1 stage given the symptoms. Terminal -2 stage given the symptoms. If you have like cancers, they talk about, for example, breast cancer, stage 1 to 4. The distribution then will be probability of stage 4 given the evidence, stage 2 given the evidence, stage 3 given the evidence, stage 2 given the evidence, stage 1 given the evidence. If I compute all of them, those numbers have to add up to 1. If they anyway have to add up to 1, I can assume that 1 over P of S, which I don't like to compute, SS, I just assume it's just equal to alpha. I didn't want to SS it. So I just assume it's equal to alpha. Then what will happen is, P D given S will be alpha times this stuff, P not D given S is alpha times, the same alpha times this stuff, another stuff. So you add these up, this is 1, this will be alpha times this whole stuff. So by the end, you know the alphas also. You see what I'm saying? In particular, actually, normally what you wind up doing is, the distribution is 7 and 10. Times alpha. So it's an unnormalized distribution is alpha 7 and 10. And the real distribution is 7 by 7 plus 10, 10 by 7 plus 10. You see what I'm saying? This is a very cute trick. The reason you should be asking yourself, why the heck did I make my life so hard to do all this computation if all I needed was just P of S? And this is, again, as I said, understanding why you do something is a lot more important than how to plug and check. Because plug and check, ultimately computers will do it for you. Why are you doing it is important. That's the reason to take this course. Okay? Why you are doing it is you are transferring assessment cost into computation. And the computers are very easy. Assessment means you have to call people. You have to go into the wild and do experiments. Those are painfully costly, even in the day of internet and all that stuff. So it's a great idea. And this is called normalization trick. Okay? And when you look at any algorithm for Bayes network, reasoning, etc., they just assume you understand this stuff. So they'll put alphas. They say, where the heck did alpha come from? Well, alpha is just this. And so if I in the end say the probability is 710, that means obviously it's not that I change the rules of probability and the probabilities can now be bigger than 1. It is this alpha times 710 should be equal to 1. That means 7 by 7 plus 10, and then alpha will be equal to 7 plus 10. 1 by 7 plus 10, right? And so these will be equal to 7 by 7 plus 10, 10 by 7 plus 10. It all works out exactly the way you expect. And what you did is, you did more computation instead of more assessment. It looks like a sucker's deal up front, right? Because a sucker's deal, if you just gave me the P of S, I didn't have to do more computation. Imagine if D can, as I said, 15 values, then you have to compute all 15 values. Not even 14, you have to compute all 15. Right? Remember, this is 2 valued, you have to compute both D of S and not D of S. Only those 2 will add up to 1. You can't just say, I'll compute P D of S, and then 1 minus that will be the other thing. Well, alpha is there, you don't know what alpha is. Understood? Okay. That's a very useful trick that people use, and you have to understand that. The second thing that I want you to understand Okay, this stuff we already told you. And I said it a lot of times, but I want to basically, you can read this, that arrow direction has nothing to do with causality. Really, from a Bayes network semantics point of view, all the arrows are telling you is what is the topological order. And if you write the chain rule in the topological order, then you can simplify this multiplication using the conditional independence assertions that correspond to the Bayes network. Okay. In particular, as you understand, in particular, joint distribution on A and B, PAB, can either be written as A arrow B, in which case you have to give P of A and P of B given A, or B arrow A, in which case you have to give P of B and P of A given B. If I were to have told you the joint distribution, you could write both of these. If you were a machine learning algorithm, you would know the joint distribution, sort of, approximately. But you don't know in the real world whether A is causing B or B is causing A. So you just toss a coin and put one before the other. And then after a while you'll forget and say, oh, arrows must be cause. You see what I'm saying? If on the other hand, you know the domain and you are actually writing the domain, network configuration yourself, you use your causal knowledge to put the arrows. That's allowed, but it's not necessary. It's very important to understand. Only people who know how the world works will know what causes what. Learners don't know what causes what, unless they did interventional experiments. Remember, anytime you are laughing your heads off, saying, of course flu causes runny nose. Really? Is that obvious? It's obvious because you read enough stuff and civilization has progressed that there is causal knowledge that's available to you. Remember, we also believe that black cats cause instant death. That works too. Instant death causes black cats. That too works. Everything causes everything. Because when we use causes in that sense, we just mean they are correlated. They happen to be occurring together. Doesn't at all mean that one is causing the other. To say whether something is causing the other or not, you need to stop the cause and see if the symptom disappears. Do you see what I'm saying? Yeah, exactly. Kill all the cats. I'm not against cats, but kill all the cats and see if you stop dying. And if you die, people will know whether or not your theory was true. That's an interventional experiment. You lose a few people. But remember, you guys, we all talk about, this is kind of important to understand. In the good old days, we could do interventional experiments on people. And a lot of our medical knowledge came from them. We don't like Nazis. It's fashionable not to like Nazis. I would be fired if I say I kind of like Nazis. But we use the knowledge that Nazis developed by doing ethically really, really repulsive experiments. They did interventions on people. The PETA people for ethical treatment of animals, think we are all Nazis. Because the current medical knowledge is based on monkeys, which is kind of us, and trying to poke holes in them and seeing what happens, what causes what, and rats. Interventional experiments is where you get the causal knowledge. In the good old days, you can try any experiment on any people. So the knowledge was improving very fast. But now it's much harder. In fact, if I need to actually do any experiments on people, you have to fill huge amounts of documentation called IRB, Institutional Review Board Certification. And when you're doing it, all of the researchers feel, oh my God, I know I'm a good guy, why are you wasting your time? Nazis thought they were good guys too. What about the other thing? What's the name of the experiment here? On the African Americans, they did an experiment. Tuskegee. We thought we are good guys too, until we found we are not. You understand what I'm saying? Because we kind of tried. Basically, people in the Tuskegee experiments, people tried to figure out what causes stuttering. For example, one of the things they figured out here was what causes stuttering. So, for example, telling you repeatedly that you are stuttering, you are stuttering, you are stuttering, does it cause stuttering? Apparently, it does. But would you like for me to find out whether or not this is true by experimenting on you? Because for your rest of your life, you'll still be stuttering. You see what I'm saying? So, getting causal knowledge is hard. Getting causal knowledge is made harder, especially in things like medicine, because we have improved ethically. We're still nowhere near, perfect, but thank goodness we don't do the random kind of experiments we used to do before. Without that, you only have correlation. Okay? So that's important to understand. The other thing that I want you to know before we end is this really deep idea which sort of makes all Bayes network stuff a lot clearer, which is factorization. Basically, I want to say that a probability joint distribution is, for discrete numbers, a joint distribution is a big matrix. You somehow want to factorize this matrix into smaller matrices, such that when you multiply these matrices, you get a big matrix. So far, so good. In fact, you have heard of matrix factorization millions of times in your life. Except we won't call these matrices. We'll call them conditional probability tables. And when we multiply them, we won't use matrix multiplication theory. We use this other idea called joining tables theory. And it makes complete sense once I show you the example. But it is in that sense. Remember algebras, right? How many of you have done abstract algebras? That you know that plus, minus, multiplication, division, the way you define it for real numbers is just one of the examples of how to define these operations. Matrices already have a very different notion of multiplication. And matrix multiplication, for example, is not symmetric. Normal real number multiplication is symmetric. So algebra, group theory tells you, all these things. So now I'm going to compute, and I'm going to define a new notion of multiplication over probability tables and show that with respect to that multiplication, you can see what is happening in the Bayes network as a multiplication of, basically taking a big joint distribution and writing it as factors, such that if you multiply those factors, you get the joint distribution. Okay? So that's what I'm going to do in the next 7 minutes, and you should obviously go carefully look at this. Okay, so I'm going to take the simplest possible network, A, B, C. A, with a link to B and a link to C. Bayes network. So by now you know that to specify this network, I have to give what is probability of A, which is 0.7, and probability of B given A, probability of B not given A, which is 0.3 and 0.8. And similarly, probability of C given A, probability of C not given A, which is 0.6. Right? I request that you indulge me and let me write this in a little more elaborate form. What I would like to write them is this way. There's nothing new. What you wrote was Z for 0.7 because the other part is just 1 minus 0.7. So what I want to write actually is for PA, I will write A 0.7, not A 0.3. It's a little kind of a probability table. A 0.7, not A 0.3. Right? And similarly for this, A given B, A given not B, not A given B, not A given not B. Right? Those are the numbers. I just write them like this. The given sign just disappears. So A B 0.3, A not B 0.7, not A B 0.8, not A not B 0.2. And the other one is like that. Now the advantage now is they're all very similar relational tables. Right? They're all basically like database tables. Okay? Except the difference is they have database tables with numbers associated with each of the relational tables. How many of you have taken database courses? How many of you know join operator? You will just see what we are doing is join. Okay? So you understand this part. This is nothing new. Then what I'm going to do is P A given the joint distribution is probability of ABC for this network. Right? That will be written as probability of A times probability of B given A times probability of C given A. In fact, what I wrote for individual entries, one of the other ways of thinking about this is, if you thought of this as A equal to true, B equal to true, C equal to true, would be probability A equal to true times probability B equal to true, given A equal to true times probability C equal to true, given A equal to true. But that rule not only works for individual probabilities, but also works for the distributions, the entire distributions. Okay? And each of these guys are little distributions. These are all conditional distribution tables. And you multiply these tables to get bigger conditional distribution tables. When you multiply them all, you will get the joint distribution table. That's the notion of factorization. Okay? So, here I wrote P of A. So basically I'm thinking in terms of distributions directly, not individual values. So the P of A is this table. I have to multiply it by P of B given A, which is this table. So I have to multiply this by this. Okay? The multiplication definition is join those tables and multiply the corresponding numbers. You know what join is? Okay? So for example, A will join with AB and you will get AB. And that row will have 0.7 times 0.3 as the probability. A joins with A naught B and will give A naught B. And that row will have the probability 0.7 times 0.7. You guys see this? This is the joining thing. So I write this, it looks like this. AB, basically A times AB is AB. That's a join. And that will be 0.7 times 0.3. A times A naught B is A naught B. And the A is the joining attribute. Right? And that will be 0.7 times 0.7. Not AB, 0.3 times 0.8, not A naught B, 0.3 times 0.2. Okay? So now notice the funny thing. This was an AB table.